I think so. We can start now. People will join later on.
Okay, so I hope you all had time to review some of the things that we talked about last week. So the plan is that I can start with a very simple 10-minute quiz online, okay, and then I can start on some other topics, okay. So what I'm going to do now is to share a link and chat, and we'll give you just 10 minutes. These are very simple questions.
So maybe, sir, you can send it over to me. Then I will share with the participants later on,
Yeah,
if
yeah.
it is
Then
okay.
I can
Yeah.
just go over it here on screen, so I can share this one. Okay, so the first question is, which wave equation is most commonly used in exploration seismology? So we have viscoelastic, viscoanisotropic, elastic, acoustic, and acoustic constant density. So anybody wants to say which one? Any volunteer?
Will it be, sir, acoustic variable density for exploration seismology?
It's actually the most commonly used wave equation is constant density acoustic, only
Okay.
one
Okay.
parameter. Okay.
Okay.
Now, if your choice of answer, for your choice of answer in question one, how many parameters are used to describe the Earth?
One, sir.
Good. Yes.
Acoustic, yeah.
And yeah, this is just the velocity, okay?
Yeah, just constant
Yeah.
density.
Yeah. And how many parameters are needed to describe a VTI medium?
Is it five, sir?
Five, sir.
Five?
Five. Yes, good. So
This is for the
here,
acoustic case.
in general elastic VTI medium, there are five, okay?
Okay. Okay.
You go over my notes. Okay, one other thing I was going to tell you is that I have some notes on the lectures that I gave last week, so I will send those over to you.
Okay, sir.
Okay, now question number 4 is shear wave velocity in water is what?
Zero.
Zero.
Good, good. So what is anisotropy? There was a question which needed a little bit of writing, just maybe one sentence.
So the property varies with direction.
Good. Stress is a tensor of rank what?
Um,
Is it three, sir?
No.
No.
mm,
Stress
there in the
is
notes. That
yeah,
was the
it's there in
first
the
thing.
notes, yeah.
So is it six independent components? But
6 is not a choice here.
Six is
okay.
not the then five.
It's a tensor of rank 2, okay? Because it
Okay.
has two directions, right? One
Hmm.
the direction of the force, and other is the direction of the normal. Okay.
Okay.
And the elastic coefficient or if stiffness in a general anisotropic medium is a tensor of rank what? Remember generalized Hooke's law?
21 something. But it was
Those are
component or rank?
those are the components.
Okay. So the
21,
rank would
yeah.
be
His rank should be 5.
Rank is 4 because stress
fourth
is
order. Yeah.
2
Yeah.
and strain is 2, and they're related by stiffness coefficient matrix, not matrix,
Okay.
the tensor. So this is basically of rank 4. We discussed that in the class last week.
Yeah. Yeah.
Yeah.
Now,
Yeah.
why is shear wave important? We didn't mention this in the class, but from your experience, anybody who's doing quantitative interpretation?
I mean, shear wave, they are more, when we want to differentiate the fluid properties, when we compare P and S, then
Yeah.
that it would be useful. Yeah.
Yeah. So what is the difference between SV and SH waves?
I think it is the polarization of the particles, the difference in polarization. If the particles are, yeah.
They're both normal to the direction of the ray in isotropic medium. So SV is is on plane and SH is normal to the plane. And the last question was, what is meant by linear elasticity?
Means the stress is directly proportional to the strain and it is
Yes.
linearly related.
Yeah, good. Okay, so these were some simple questions. I thought we might just go over those. The quiz part is over. Let's start with the first lecture. And so in the first lecture, we will basically look at something called Green's function. Okay, so there are some concepts that I'm going to describe here, which are very, very important. And that is why I wanted to start with the discussion on Green's function, that is fundamental solution to the wave equation. And we'll look at analytic solution. And again, math is all in the slides, so don't get intimidated. These in the mathematics here is not all that difficult, just that it looks complex because of the notational problem that we have now. So the outline or the topics that I'm going to discuss in this particular lecture include a Green's function, and I'll tell you what Green's functions are, and then plane waves, then relate those to Taupy transforms, and there's one other concept that you may be familiar with. It's called angle gathers, which are used quite extensively in inversion, especially for AVO kind of work and imaging. So first, I wanted to give you a simple derivation of acoustic wave equation, which is no different from what I talked about earlier. Last week, I gave you a more general derivation of the wave equations for elastic, anisotropic, even viscoelastic medium. But here, we'll just assume that the medium is acoustic or water-like. Okay. So here, the parameters we'll use are your things like mass of the fluid. Okay, so here we have the density, and this is the particle velocity of the fluid, and that we normally don't measure, but it figures in the equation. But what we measure is the pressure. We cannot measure, vector particle velocity field. So in any case, so there are two components, x and z, and this is your Newton's second law of motion. Okay, this is the gradient of pressure, and this is the velocity. Okay. So velocity, derivative velocity with respect to time. So this is your acceleration. Now here, we just rewrite this equation to get a new equation, and now we bring in our stress-strain relationship and plug it in here, and that gives us this equation, okay, for a constant density. Because in this equation, the density is within the bracket and on which you are applying, of which you are taking derivative. But if density is constant, this actually comes out, and k over rho, square root of that gives you velocity, okay. So that's our velocity, the wave equation that we have been dealing with. So this describes your pressure P as a function of x and t, as to how the pressure is changing with respect to location and time. So you can think of this as you go to a pond or a swimming pool and you drop a pebble. So that's your source. And then what you see are some wave fronts propagating away from the source in circular arc, right? And those are essentially your pressure fields, and it shows you as a function of distance from the source how the how the waves are propagating, so how the pressure is changing, and also as a function of time. So now the question is, this equation really does not tell you that. We have to have a solution for this equation, essentially solving the PDE. And we will do this for a homogeneous medium, okay? So first thing we will do is we'll take a Fourier transform. You're all geophysicists here, so you're familiar with Fourier transform. So this is our uh, time domain pressure field, and this is the kernel of the transform. So you integrate over time, and that gives you the wave field in space and frequency. So if you did that, then you get a equation that looks like this. So there is no time here, which has been replaced by frequency. And this term, k equals omega over v, is called wave number. Okay. Now you can do another transformation from x to kx, which is wave number. So here is your forward Fourier transform going from time to frequency. And we have to do, in 2D, you have to do a two-dimensional Fourier transform here. This is basically kx and kz. These are the wave numbers in the x and z directions. So you take this wave field and take this two-dimensional derivative. In 3D, it will be three-dimensional, and that gives you this equation. Okay. And here, kx squares plus kz square is nothing but your wave number squares. And this is called dispersion relation. So what is Green's function? A Green's function is basically the solution of any PDE, a homogeneous differential equation, whose forcing term is a delta function. So for example, in our case, we have your previous equation, this, and then we have a forcing term, right? F. So if this force is a delta function or a spike, then it gives a solution that is called Green's function. And why are we interested in this? The reason we are interested in this is that for any other force, you can just convolve your Green's function with that force term, and it gives you the solution for a different source. So first of all, the reason we are interested in getting into the Green's function is we want to know what is the nature of the solution in a medium that is perfectly homogeneous. Okay, and then our interest is in inhomogeneous medium, but first we have to understand what happens in a homogeneous medium. So that's your equation for Green's function. This n indicates the dimension, and this L is your differential operator. And this is in 1D, this will be your partial differential equation whose solution is G, and this G is Green's function. So the Green's function is the solution of the wave equation when in the right hand side you have a delta function in x and delta function in t. For those of you who may not be remembering what delta functions are, direct delta function, practically speaking, is a spike at one location. So this basically means that at x equal to 0 and at t equal to 0, there is a source term that initiates the motion. All right. So how do we solve this? Well, in 1D, we just essentially go to Fourier domain, and in Fourier domain, the solution is very simple, and then we take inverse Fourier transform, and that gives us a solution that looks like this. Now, the most interesting thing is when you actually, it's also evident in the frequency domain, but you don't see it, obviously. But if you just go to the time domain, what you see is that the solution is given by this term. So what is H? Anybody knows what H is? H is a Heaviside step function. So if you have a delta function as the source, it turns out that the solution is a step function. Okay. So 1D Green's function is a step function because in one dimensional, the wave from a point source, it maintains its amplitudes forever after it passes. Okay. This is of no interest in general for us from practical point of view because we're never dealing with 1D. Now we go to 2D. In 2D, everything is the same. Algebra is it's the same. Only thing is that when you do the Fourier transform, at the end, you get a solution that looks like this. And here, what we have is quite interesting. Even though you have this step function, what you see here is a term which is v squared t squared minus r2 squared. And what is the implication of this? And I will explain to you with a figure a little bit later. So this, actually what this does, it allows amplitude decay slowly as t goes to infinity. So yeah, we'll have the figure later on. But in 3D, once you carry out the same algebra, just take Fourier transform and then do the inverse transform, you get a solution that looks like this. This is something you are familiar with. Because all this means is that it's actually goes like a spherical wavefront, and the travel time is, this is a spreading term, and this is the time dependence, okay? So the time dependence would be delta function, okay? So at any distance r, a delta function propagates as a delta function when it comes to 3D. So once you look at the three results, this is a Green's function for 1D, this is a Green's function for 2D, and this is the Green's function for 3D, okay? So once you inject a pulse in 1D, this is a step function. In 2D, it's got a decay, and this decay is square root of 1 over square root of t, okay? And this is a 3D Green's function. Did anyone in the group know this already? Is there anybody who didn't know this? I'm asking you guys. Did you already know these differences? And why am I even talking about this? How many of you have done migration?
I think Santosh.
So
Santosh
I
has
think
done.
this is migration uses this function, right?
So in migration, what we do normally, actually remember this, I'll come back to this in a second. Okay? And I'll explain to you why I'm mentioning this. But this is a very important result that you should pretty much memorize. Now this brings us to some definitions, some concepts that are very important for seismic data analysis. You know, you hear this term 1D, then you hear this term 2D, you hear this term 3D, and so on. When we say 1D, pure 1D is actually talking about plane layers and plane waves. So this is what we're talking about in this case. Essentially, the closest thing that comes to our mind is the post-stack scenario, where a normal incidence plane waves basically goes up and down the layers, okay? But what we're also interested in is pre-stack, right? When you have a point source and we have a bunch of receivers. And in geophysics or exploration geophysics literature, this is generally known as 1.5D. All right. Now in 2D, when you talk about 2D, what it assumes is that the structure is varying in 2 dimensions, but what about the 3rd dimension? The thing that you have to keep in mind is that real world is 3D, right? We have 3D and we have a point source, but we are approximating it with different dimensions like 1D, 1.5D, 2D, and so on. So when you say 1D here, 1.5D, that means the medium is cylindrically symmetric. So that means if you go azimuthally, the medium remains the same, okay? The same thing applies when you say 2D. This is a 2D cut. In 3D also we assume symmetry, okay? So in 3D, essentially what you're doing is we're using a line source, And like point source in 1D, the spreading is 1 over r. Okay. Now, when you have a line source in 2D, your spreading is 1 over square root of r. Okay. And this is something that comes out of the Green's function, as you saw already. There is a decay. This is the spreading. So this is not spherical spreading. This is generally called cylindrical spreading. So now comes to seismic processing. So let's say that you have a 2D line, right? And you want to use a 2D algorithm to process the data. In reality, the Earth is 3D and you have a point source. But as soon as you restrict your algorithm to 2D, it becomes line source. So that means you have to either correct your algorithm to handle 3D spreading and the t to the power minus half decay, or apply the correction to your data so that it becomes 2.5D. Okay, so 2.5D would mean point source in 2D, which is this is not exact. Okay, this is approximate. Now in 3D, you have a point source, and this is 1 over r, and this is your reality, except that we haven't talked about heterogeneity yet, and which is going to come next. Now, this is the reason why I wanted to show you what Green's functions are and why they are useful. Now, the Green's functions that I've shown you have analytic solutions. The reason they have analytic solutions is because we assume that the medium is homogeneous. But even if the medium is not homogeneous, you can find Green's function with a point source on the right hand side, just that it's not going to be analytic. It's going to be either pure numerical. Again, putting a delta function in numerical algorithm is not possible. We'll talk about that later on. Or you can use approximate analytic solution like asymptotic ray theory. Okay. So this is your takeaway slide, which you must remember. So now we talked about plane waves. We talked about point source. So let's formalize it. So here, when you say 1D layered, this is plane wave, 1.5D, point source, 2D is line source, 2.5D is approximate correction to the line source that gives you 3D. So this is 2D geology and real point source. And of course, this is the most realistic scenario. You don't have to apply any correction to your data. It's full 3D survey and migration. Okay. So now a little bit about plane waves. I did mention plane waves last week when we talked about anisotropy. So let's revisit. So plane wave, essentially the wavefronts are planar. Okay, so here we have the displacement for the vector wave field. This is the direction of particle motion. This is the amplitude, and this is the phase term. Okay, and this p is the phase velocity based on our discussion last week for a general anisotropic medium. This depends on the direction, and here this particle motion is also not normal to the direction of propagation in anisotropic media, but for isotropic case, we know that p wave is polarized along the wave propagation direction, and S wave is normal to that. But this is the most general representation of plane waves. Now, why are we interested in plane waves? The reason we're interested in plane waves is because these are basic building blocks. So our cylindrical and spherical waves that we talked about earlier in terms of Green's function, they can be constructed as a superposition of plane waves. Okay. So now you can look at this particular picture. This is a 2D slice from a 3D volume. So this is a circle, which is a basically vertical cut of the sphere, and these are different wave fronts. So as you go outward from the center, this is basically increasing in time, right? Now, if you observe a spherical wavefront for a very long distance, this appears like a plane, right? Now you can think about these. If you just draw a ray path here and draw a tangent to it, this will give you a plane wave. So another ray path, another tangent gives you second plane wave, and so on. So summing up all of these plane waves then give you the spherical wavefronts. This is one thing you can understand without actually doing any math. Okay? But in the field, we observe, say, in a homogeneous medium, we would be observing spherical waves. That in homogeneous medium, those wavefronts would no longer be spherical; they'll be basically changed, depending on what kind of inhomogeneity it encounters. Now, can we actually observe plane waves in the field? The answer is not really. In fact, a long time ago, Amoco tried to do some experiment where they tried to generate plane waves in the field. What would that mean is that if you have on the surface, you can have a whole bunch of shots. They're fired simultaneously, and that will basically give you a p equal to 0, right? And this is normal incidence plane waves. Now, if you fire these shots with a delay in time, then you can generate plane waves at a different angle, okay, and so on. But this is very, very expensive to do it in the field. But then plane wave analysis seems to be quite useful because those are the basic building blocks. So can we actually take our field data or our point source data and turn those into plane waves? And that is what is done using plane wave transformation. So spherical waves can be expressed as a superposition of plane waves. And so this is what I meant. So here, if you have this equation, remember, this is our Green's function, 1 over r, and this is our travel time. And in the Fourier domain, this is what it looks like. And so directly, your Fourier integral gives you your plane waves here. The sum of all the plane waves will give you this. So now going backward. So if you take the point source to do a 3D Fourier transform, that can say give you plane waves. So let's see how we can do that, or we can go from plane waves. Then how do you go from plane waves to point sources? Again, inverse Fourier transform in 3D. Okay. But in practice, we use something called tau p transform. Okay. So in tau p transform, this is what is normally used. So here you have the integral in terms of kx and ky, and you can turn this into k equals omega times p. Okay, kx equal to px times omega. If you did that, then you have this, and so this basically, so it turns out k is equal to omega times p, and this p uniquely defines a plane wave. Okay, and for basically in 2D, let's say if you have data only along x direction, you can set y equal to 0, and this gives you this particular integral. So if you take this and apply Fourier transform, at the end what you get is t minus px minus tau. So and that basically gives you an equation in tau px minus t. So you take the data and you apply this transform, and that gives you a tau p gather. So here is a plane wave, and then we have these different angles, and these are different tangents. These are different plane waves corresponding to those angles. And this p is essentially sine theta of v. Okay, this is also called horizontal slowness. Now this concept becomes very, very important. So let me ask you this. What is Snell's law?
Yeah, I mean, the Snell's law says that P remains constant as the ray progresses.
Very good. Very good. See, this is what many people forget. They say, oh, sine theta yv equal to sine theta 2 yv2 or something like that. Bottom line is that whether it's isotropic media or anisotropic media, Snell's law basically means that horizontal slowness is preserved. Okay. So geometrical transformation from offset gather to tau p gather would simply mean that, so this basically represents a straight line, right? T equals tau plus px, and this tau is intercept and this is the slope. Okay, so these are your reflection hyperbolae, and the tangent of this would be your p. So what is the unit of p?
It's basically intercept, I think. Intercept.
Intercept is tau.
Yeah.
P is the ray parameter.
So slowness
what is this?
It's slowness inverse of
it's slowness,
velocity.
inverse of velocity. Yeah.
Exactly. So this is second per kilometer. Okay. Yeah. So what you do here is, let's say, so this is a typical data. So you have the direct wave, then you have this reflection. So at any point you have this p value. So the way it works is that for a given t, you basically shoot a whole bunch of angles and take all the amplitudes along those paths and then place it in tau. So it's just the binning of the data from xt to tau p, but the stacking is done. Why is it called slant stacking? Because the stacking is done along the slanting direction. Okay. So if you have these events here, and this is your direct wave. So what does it look like in tau p? So this direct wave basically propagates with a constant velocity, right? So it has only one slope, and that maps into a point. A direct wave will map into a point. Head waves will map into a point, but your reflection hyperbola would map into ellipses. Okay, so these are elliptical. Now you can think about, say I have a layer, I have an interface here. This is a reflector, and I'm shooting a ray. So normal to the ray for isotropic medium, this is your plane wave front. It's given by ray parameter p, which is basically sine theta over v of this layer. This is your v. So p is your sine theta over v, and q is your cosine theta over v, and therefore p squared plus q squared is equal to 1 over v squared. Okay, so here your delay time is 2 times the layer thickness times the vertical slowness. So in other words, this is a very interesting concept. What you're trying to do is, if you want to know the travel time here, you need to, this is a sum of 2 paths. This is the vertical delay time, and this is your horizontal delay time, which is p times x. And then sum of the two will give you the total travel time. Okay, this horizontal time and the vertical time. Vertical delay time is your tau. Okay, but in general, when you are in 3D, you cannot just do a simple slant stacking. Your argument, or rather the kernel in your transform, is actually a Bessel function, and you can take make some approximations of that. But those are some of the details I'm not going to go over. You can look at my notes, and then we can discuss later on if you're interested. Okay, so
Sir, I have a small doubt here
Yeah,
on the topic.
please.
So
Yeah.
normally, like in our routine data processing, we do a copy for a number of things for noise attenuation, for deconvolution, and all those things. So is
Yeah.
there any chance that there's a chance that we lose the amplitudes when you do just a forward and reverse copy and do some operation in the copy domain? Does the amplitude of the events gets affected by
Yes.
any means if you're not
Very good.
careful or something?
Yes, it will be, because if you just use a simple copy transform, then it assumes line source, right?
Right.
Depends on what kind of So there are three different ways. We just showed you simple line stack. Okay, so it basically does not give you the true amplitude if you go back and forth. Okay, now if you use a true plane wave transform, not the Topi transform, which basically whose argument is Bessel function of some form, depending on what kind of, let's say for acoustic medium and pressure sources, it's a zeroth order Bessel function. Then you can get the correct amplitude back and forth. In fact, I remember when I first joined as a faculty member, I was very young then, and I had a student who I assigned to do Taupi analysis of some data, and one very well-known professor from a department basically scolded him. He says, "Don't do Taupi, because if you do Fourier, forward and inverse transformation, the amplitude is not preserved." So the student was very nervous. He almost crying that, he told me to do this, but this professor is telling me that it's totally wrong. I said, he's telling you that because he does not know how to do it correctly. And then I showed him, and then we generated some data. We applied it to data forward and inverse transformation using the correct method and the incorrect method. And I was able to demonstrate that if you do it correctly, you can preserve the amplitude, except for the filtering part that we do. Okay, to get stable transformation, sometimes you have to apply some filtering. That we understand. But if you do it right, using correct argument in the integral, you can get the correct amplitude. Okay, so that's very important. Very important.
Thank you, sir.
Concept, and I'm glad you asked me that. So now
Thank
the
you very
question
much.
is, so why is Taupi transform important? Is that it takes your data from point source to plane waves. Okay, so plane waves do not spread, right? So with Taupi transformation, then plane wave transformation, I shouldn't call it Taupi transformation. Plane wave transformation, you can actually get spherical spreading already corrected for without having to know the velocity. Another thing is that if you still assume layered medium, your multiples are truly periodic. Okay. In XT domain, they're not periodic. In Taupi domain, they are periodic. So applying a deconvolution filter to eliminate the multiple in Taupi domain works much better than applying it on the offset time domain. Any other question?
So, sir, there is a question.
Yeah.
So when we use, let's say, a Kenneth-based inversion, then our input data should be corrected for the spherical divergence.
Right.
Is it?
Yeah. Okay. So depends on which version of Kenneth you are using, but which kind of inversion you are using. But in my code, I do it in Taupi domain. So, but so that means I take the data and I transform it to Taupi. So it is already corrected for spherical spreading.
Okay. Thank you, sir.
Okay. So these are some details of transformation artifacts as to how you choose delta P and things like that. So this shows you, like, depending on the maximum offset and frequency, you can choose what the delta P would be. Otherwise, there'll be some kind of aliasing. Okay, so one important thing. Again, I will revisit this today only. Reflection coefficients. We talk about that a lot. Do you realize that if you look at the derivation of Zopf's equation and any other approximations thereof, these are functions of ray parameters. Okay. So in top E domain, you can actually look at the amplitudes as represented in reflection coefficients. It automatically corrects for geometrical spreading. And under 1D assumptions, the multiples are truly periodic in all P's. So the predictability curve works the best. So sometimes we use something called parabolic radon transform, but this is actually a different concept altogether. And I've seen some people applying this algorithm for trace interpolation, regularization of the data. Then it's very unfortunate that in the industry, people don't want to hear about plane waves and tau p. They want to hear about angle. And angle is essentially known only if you know the velocity. Because remember, P equals sine theta over V, right? And P is the most fundamental parameter, even in anisotropic medium. Actually, I wrote a paper on that a long time ago. So this, if you know the velocity, you can get to angle. Otherwise, you don't. So that means you have to know the velocity. And people understand better when you talk in terms of angle. But angles and plane waves, they're not the same concept. Say, for example, if you take simple two-layer case, okay, and you're looking at reflections. So this, then same offset. Now the second one that goes through here and comes back. So this one, this P and this P are different, right? But this angle and this angle can be the same, right? So that is something one has to remember, that in XT domain, the angles that you're recording are different for different times, or different reflectors, okay? So you have to be able to sort it. And if you know the velocity, you can do this mapping. And I'll talk about that. Okay, so one question. I remember many years ago, I was giving a talk on tau p transform. And then one person from the audience said that, oh, but it does not apply to an anisotropic medium, which is completely wrong. It does apply. In fact, it is more useful in anisotropic medium than in isotropic medium even, because, in anisotropic medium, the velocities are dependent on P, a ray parameter, or the angle. And so for anisotropic analysis, tau p is even more important. Okay, so like I just introduced you, or rather I just mentioned in passing about angle gathers, right? So how does one map from offset to angle? So let's say that you have this geometry, we have a point source and we have the receiver, and this is your CMP geometry, and we know this is at some angle, say 24, 34, whatever it is, depending on the velocity and depth, depending on the depth and offset. Typically, we use X as this, and this H is the half offset, and the reflection angle is theta, and here RMS velocity, let's say, is V. Now, we need interval velocities to be able to exactly map it, okay, to angle. So given this NMO equation, you have RMS velocity, and then you use the Dix velocity, for example, to convert it to interval. And using that, you can now compute this angle. Because to be able to, or in other words, to know the angle, you have to know the depth of the reflector, right? And this depth is not known. What we have is time. And time and velocity, these two combined can give you the depth, right? So we have to know what the velocity is. And the easy way, not necessarily the correct way of getting this, is using RMSs to interval using Dix equation. And once you get the depth, you can get the angle, okay? And then they're saying that in general, then people would compute P from here. So this is sort of like a roundabout way of computing P. On the other hand, if you simply did a plane wave transformation, you have the gathers in P, and you can map it to angles with the known velocity. To go to angle, you have to know the velocity. And this is where you have to be careful. In anisotropic medium, you have to know velocity as a function of angle to be able to get to the angle. Okay? And how do you know that to start with? So you have to know the full elastic tensor to be able to do that. Okay. Nonetheless, angle gathers give you very useful processing sequences, and a lot of good stuff has been done using angle gathers. So it's important that we learn. So here, let's say that I have the offset gathers for different layers with different velocities. And the first thing we do is apply NMO correction, and then we get to this angle gathers. Okay, so here I plot this as a function of angle. Now, the way you do this offset to angle gather is essentially from this kind of a table. Okay, so you need these shallow reflectors reach large angles at short offsets. This is very important. Deep reflectors require longer offsets for equivalent angles, and velocity controls the curvature of the offset angle curve. Okay, so typically we make use of angles in the range 0 to 45 degrees, and beyond 45 degrees generally it's post critical, so there is a phase change, and that is kind of hard to handle in a standard processing algorithm. So the step-by-step workflows with the convert the data directly, you typically follow these steps. Velocity model definition. So you have to input the velocities. Sometimes you can also take if you have several well logs, you can just interpolate and extrapolate and generate a velocity field. That will be your interval velocity directly. You can just convert from RMS to interval. And of course, you have to apply NMO correction because you just want to pick those and show those as a flattened gathers. And that's what is used in AVO. And this is essentially ray tracing that gives you those angles, and then you can do angle binning. So typically what is done is that we generate angles like 0 to 5, 5 to 10, 10 to 15, and so on, and then we stack those. And these are called angle stacks. And the reason you stack those is because that has higher signal to noise ratio. Now, I would not ever use 0-degree angle because we don't ever record normal incidences. So, typically you start with maybe 5 degrees, okay, depending on how close you are to the source. Okay. So these are the steps to generate angle gathers, and then of course, you can run different kinds of analysis, and the reason they are useful is that we can use those for AVA and AVO analysis for fluid and rock identification, because as the angle of incidence changes, the amplitude actually changes depending on the contrast between different layers, and that actually revolutionized the way we were looking at seismic data. Earlier, all seismic data were basically stacked data and was mostly used for interpretation. And then came your bright spot, where within the stack section we saw some bright anomaly. Now, to be able to explain that, you had to go inside, and then people discovered something called amplitude variation with offset or angle. But this is something that was done in classical seismology long time ago. But this becomes really important. These concepts become really important when you actually observe those in field data, and those observations can tell you something more meaningful. In this case, fluid and rock identification. So AVO technology then became absolutely like a great invention until we came up with much better algorithms which are still in the works, like elastic FWI. And one other use of angle gathers is in imaging. So these are used as a diagnostic tool. So what you do is, after you have migrated your data, as a pre-stack migrated, then you actually generate angle gathers, and you actually plot those panels, angle panels, just like the way you see NMO move out. In angle domain, you look at the move out, And if it's not flat, that means your velocity that you have used in migration is not correct. You have to apply some corrections to the velocity. Even this is even used in FWI as one part of the loss function or objective function. So flattening the angle gathers is one criteria that is used for estimating velocities in migration and also sometimes in FWI. Okay. So, this is a typical case of how one goes about doing AVO analysis for different classes of AVO, and you can plot those in intercept gradient. And again, this is something I'm sure you know much better than I do because you have been doing this regularly, but these are some of the reasons why you want to look into angle domain gathers. So offset to angle gathers, NMO velocity analysis, then you do Dix inversion for interval, you depth convert, sometimes you migration to depth, then you do angle computation and then angle gather binning, and from there you can actually extract AVO attributes. Okay, because now there's a reflection coefficient which I'll probably talk about in the next set of slides is what is used for rock property analysis, and that can be represented as a function of angle, although fundamentally they're basically functions of P. Okay, so here is an example from real data. This is your CMP gather offsets, and then this is NMO corrected, and then this is your angle gather. Okay, so this is done routinely. You can do this in Hampson Russell and many other software packages, but it's important to understand how it works. And sometimes if you have residual NMO, that gives you really bad angle gathers, so you have to be careful about that. Okay, so the key takeaways from this particular lecture is that in the offset gathers, they record amplitude as a function of source receiver separation, and you have hyperbolic move out. Angle gathers, these are derived by mapping offset to incidence angle. Common image gather flatness of that basically validates whether the migration velocity is correct or not. In which case, like flat velocity would give you correct velocity, flat CIG. If you're not familiar with this acronym CIG, it's called common image gather. So flat CIG means velocity is correct, and if it's not flat, then you have to change the velocity to get the correct migration. And AVO is done in angle domain, and typically we go from 0 to some 40 degrees. Okay, so this concludes my first lecture for today. If you have any question, please unmute yourself and ask.
So let's say we are transforming our offset to angle domain, so we require velocity. But for a tau p transform, we don't require velocity as such.
Tau p transformation, we don't need velocity.
Yeah.
But if you want to go to angle from tau p, then you need velocity.
Okay.
Okay, can you see the PowerPoint?
Yeah. Yes, sir.
Okay, so we start with some very basic modeling now. So we talked about homogeneous Green's function. Now we talked about plane waves and things like that, and we talked about 1D, 1.5D, 2D, 2.5D, and 3D. So I think the best to start with post-stack case, which I'm sure most of you are familiar with, even though it's a very simple case. In terms of theory, in terms of actual implementation, it can be difficult to interpret often. So for post-stack data, you have this pre-stack gather, and then what you do here is so you apply NMO, and then you actually mute very high angle or very high offset traces. Then you stack those, and that gives you a seismic trace. Okay, and this is basically from different CMP locations. You line those up, and then we say that this is kind of representing sort of geology, and we know that it's not a real geological description, but we'll have to do some processing beyond that, but that's something we'll not talk about right now. So we have this post-stack seismic section, and what we try to do is to invert each trace here and try to get some subsurface properties. Okay. One thing you have to be careful about is what kind of amplitude am I getting here by stacking. So this is called a full stack, where you are basically stacking all the traces from all offsets. But if you are interested in amplitude analysis and calling it a post-stack or normal incidence, then you should not be stacking all traces, because basically there is interference from AVO. And here, if you stack within small angles, you can see the amplitude is very different from if you were to stack the entire offset gather. Okay. Now, the first thing we want to do to be able to invert is to model. I will not say yet as to how we are getting these reflection coefficients. So this is your model parameter is P impedance, which is velocity times rho for those who don't remember. And you can see that step function impedance maps into two spikes. And our model for forward modeling is a convolution. So what is the amplitude of these reflection coefficients? This is essentially the contrast in impedances. So Z2 minus Z1 by Z2 plus Z1. And it assumes small contrast. And in this convolution model, we assume that there are no internal multiples. So we take this and convolve it with a wavelet, and that gives us a seismic trace. This is our synthetic seismic trace. And we can look at the wavelet amplitude and phase spectrum to see what kind of wavelets you have. And then, of course, iteratively, we try to match our post-stack traces with our synthetic to get our acoustic impedance model. Now, this is a paper that was published a long time ago, 1961. And before most of you were born. But this still remains a very important paper in terms of understanding post-stack synthetic seismograms and their implications. Just wanted to remind you that all the calculations done here assume the density is constant. So essentially, your delta V is what gives you those reflection coefficients. Nonetheless, all the interpretation and implications still remain valid. So here, the theory is that it assumes a linear filter model. But by the way, is there anybody in the audience who does not know what a convolution is? Anyway, if you don't, just need to teach yourself. It's very simple. If you have a 2 time series, let's say F T, another time series GT, a convolution would simply mean shift, multiply, and add. Okay. So in this case, this QT, a GT would be your reflectivity sequence, and this will be your wavelet. Okay. So here we assume that the layering is described by a velocity log. The short pulse is time invariant, and it propagates as a plane wave, and multiples, ghost, and other noise are negligible. So a standard method is what is called impulse response. So it's basically the input that will produce a transient waveform, as the output of this waveform is called the impulse response. Anyway, that's just technicality, but this is what it looks like here. So let's say that you have an impulse here. I'm glad I have this particular picture because delta function is really not a realistic function. It basically says that delta t at t equal to 0 is infinity and is 0 elsewhere. It's highly localized and the sum integral is equal to 1. Now the way it's approximated is basically with the boxcar function, and then you shrink the boxcar to a very small delta t, and that gives you your delta function. So if you have a filter here, and if you run a pulse as an input, this output will be called impulse response. So you can think of this as if there was this impulse response as an input, and you run it through another filter, which is your earth, and that gives you your normal incidence seismic trace. Okay, so here, this is what I'm showing you. This is a convolution, which is basically this is the shift part, this is the multiply part, and this integral is the add part. Okay, so let's say that this is your input, and that's your filter, and that's your output. Okay, so depending on the nature of the filter, your output changes, even though input stays the same. So this is another input, this is another filter, and this is another output. Okay, so this property shows that for a given input in material, which of the two waveforms is considered as input and which is considered as output. Okay, so which is considered as input and which is considered the impulse response. So what it means is that convolving, let's say I have a source wavelet, okay, I'm calling it WT, and I'm convolving it with RT, which is my reflectivity. In fact, this is small r. Okay, so if I put it in this integral, this will be my W tau and this will be my R tau. So it means I'm shifting R and I'm multiplying with FT, and F tau stays the same, right? But it really doesn't matter how you do this. It could be RT convolved with WT, the result would be the same. Okay, here comes the interesting stuff. So let's say that I have an earth model with just one layer. Okay, this is the depth, this is the velocity. So first thing we need to do is to compute the reflection coefficient, and I also need to know the time here. Okay, and this time is essentially your 2 times depth divided by velocity. Okay, and this reflection coefficient, since the density is constant, is V2 minus V1 by V2 plus V1. So what does a convolution give you? So at t equal to 0, this is your initial pulse, this is your wavelet. Okay, short pulse. And then after time t1, you get an arrival. So the question that I have here is that, do these amplitudes look the same? Yes or no? Anybody wants to?
I think they differ in amplitude, sir.
Yeah, and why is that difference?
Is it what would this?
Because what gets reflected. Yeah.
Sorry,
go ahead.
Sorry, sir.
Yeah.
Is it because it's because of that? What do you say? It travels the time variant issue.
There is no spreading here because this is a plane wave, right?
Right. Yes.
And there is no attenuation.
So it is the impulse response of the earth. I mean, it is interacting with the earth.
This is basically reflection coefficient, right?
Yeah.
So you take the initial pulse, and that basically gets the amplitude. So what does this R mean? It means basically the amplitude of reflected wave, right? So this, what it means is that a part of the energy that hits this reflector gets reflected, and the remaining actually gets transmitted, right? So that's why you don't get back what you're sending in. And this is important because this reflection coefficient depends on the velocity contrast, right? So different kinds of geological layers will have different velocities, and based on that, you will have different amplitude pattern. Okay. Now, if you have multiple layers, for each one of those, you have to have a reflection coefficient. So first thing you do is you have to generate a time series, right? This is your two-way time. And then this is your reflection coefficient. And then you have this times, you have one here, one reflection here, reflection coefficient there. It all depends on the contrast, okay? And this could be negative also if we have a drop in velocity or drop in impedance, okay? So that's one part. So if this were all spikes, it'll be so nice for us, because then we can interpret in terms of actual layering, right? But in reality, we have the wavelets, so that basically masks a lot of information. So what you do is take the velocity, you convert the depth to travel time, two-way travel time, which is function of t, and then this is basically computing reflection coefficient. In this case, it's logarithm of v, but it's actually logarithm of impedance. And this gives you your reflection coefficient, okay? So if you have these different depths, you can have reflections showing up like this, okay? What do you see here that is different between these pulses coming from different depths?
Is it the frequency content of that? It's becoming broader as the pulse travels down.
Good. Okay, so in practice, when the pulse travels inside the Earth, the amplitude is given by the reflection coefficient, but then your pulse gets filtered. Earth acts as a low-pass filter, so it actually filters out higher frequencies. So in other words, there is attenuation and dispersion through the medium, and this is given by Q, right? And our model, the convolution model that I'm talking about, it assumes that the wavelet does not change, okay? So this is called stationary convolution. That means it assumes that the wavelet is not changing with depth. Ideally, we can either include a Q effect in here or actually change the pulse as it goes deeper inside the Earth. So not to make our life complicated, typically we focus on a small zone within the say reservoir depth or within the thickness of the reservoir plus minus something, so that we can assume safely that the pulse has not changed within that layer. Otherwise, you'll have to include this. And convolution model, the way I just described it, does not include that. Okay. Now we have to see different kinds of effects. So for example, if there is a sharp, just a delta function in velocity, there's a step which is like a layer jump, or you can even have continuous change in velocity and densities, which is like a ramp. So how do they look like? Okay, so this is a very nice demonstration of convolution. What we have here is simply a layer, and there is a homogeneous layer above and homogeneous below. So you can think of this as this is basically increasing depth or increasing time. And these two interfaces, the discontinuities and velocities in time, would be T1 and T2. So what we have here is from left to right, there's a gradual decrease in the thickness of the layer. This is pretty thick. This is thinner than that, and this is very thin. Okay? And now you are propagating one pulse. So what happens here is that from top layer, I have a positive reflection, and from the bottom of from top interface I have a positive reflection, and from the bottom I have a negative reflection. Now let me remind you, reflection coefficients are interface properties. These are not interval properties. Okay. So this is from the top layer, which I have a positive pulse and I have a negative pulse. Now the time series will be sum of these two, and what you see is that when the separation between this is far greater than the period of the pulse, you can see two distinct pulses. On the other hand, if the thickness of the layer is 1/2 of the period, they interfere and you have a high amplitude, and this is the tuning effect. Now if your layer is even thinner than that, you can even have a destructive interference, and you have a weakening of the amplitude. This is a very good example of what you can expect in your data, because our layers are not flat. I'm sorry, our layers are not thick, and thickness is actually, just excuse me. So thickness, when you talk about thickness, it's all relative to the pulse that you're trying to investigate it with. Okay. If everything was thick, then they'll be very well resolved. But for thin layers, we always get composite reflections, and depending on how thin it is, you can either get a tuning or you can get some kind of differentiated short pulse.
And also, so the phase also changes. I mean,
Yes,
if it is
phase
very
changes.
thin, yeah.
Yes, the phase. So this is the next thing I wanted to point out, and I'm glad Ashok already kind of hinted at that. Now, given, say, this or this, how can you tell what the wavelength is, or how many interfaces are there? Right? I can assume that this is my wavelet, right? And I can perfectly match the seismic trace with simple one interface, right? I can do the same thing here. So deriving the wavelet is never recorded in the field. I think there are only few cases where they have recorded the actual source time function in the field, but then normally not recorded. So then where do we get it from? Because a lot of these analyses require that you know the wavelet, right? Only if you know the wavelet, you can essentially talk about different interfaces and different layers. So if you look at Sherif's dictionary, he talks about wavelet as a pulse that is completely isolated. For example, one from seafloor, but seafloor can also be pretty complicated. In marine data, you can look at the direct wave and you can estimate the wavelet from there. Otherwise, you have to determine this sort of statistically. So this is a very important figure. Okay. Now, here is another one. This is the transition zone. So what I'm showing you here, this is a layer with two interfaces and one layer. And here, what has been done is that this jump in velocity from layer 1 to layer 2, this is a sharp jump. And as you go from left to right, we have actually made it more and more gradual. And then we tried to look at synthetic seismograms for this kind of layering with different pulse widths, okay, or different frequency content. I mean, you can look at it forever. I mean, just look at it for hours and you learn so much from this particular picture. And they're very useful for interpretation. When the layers are, or the interfaces are well isolated, even if the frequency is decreasing, you are able to see this two interfaces very clearly, right? On the other hand, as you go to lower and lower frequencies, what you see is that they become broader and broader, and you can't tell the difference. And so this is kind of important. When you have at very high frequencies, this transition zone is actually missed. Okay, say for example here you are only seeing this, so you're not actually seeing a reflection here. Now there is some other theory that tells you that there can be some reflection from second order terms, but that's very weak. So as you go to low frequency, you are beginning to see some of these. And why is that the case? Can you tell me why that is the case?
Maybe, sir, at 48 millisecond pulse, this transition is acting like a sharp change.
Good, very good. So this definition of interfaces and this thing is actually very much dependent on the frequency that you are proving it with. Okay.
And also one point, sir, that this figure shows that we require all kind of frequencies to actually image the Earth, not just high frequencies.
As many frequencies, I mean, as the broader the band, the better it is, but there is a limitation, right? Because we can't really have all high frequencies going all the way to our target depth. Okay.
Right. Yeah.
So this is very simple model, but it's so important that it tells you a lot about what can be expected from seismic data, right? So this is one of my favorite papers, and this shows you same thing, but with the tuning. And back in 1961, this gentleman or these authors, they generated synthetic seismograms. This is the field record, and this is your synthetic record. Now we take this for granted, right? Oh, we just put in some interfaces, convolve it, and I have the synthetic seismograms. So imagine this was a major breakthrough in that we could actually generate synthetic seismograms and compare it against real observation and talk about what the subsurface reflectivity should look like. Okay, so this is your field record, and this is your synthetic record, and that's your velocity function. And nowadays we do this routinely using a whole bunch of well logs, load the seismic data, and we tie the wells and all this nice stuff. But this was done many years ago, in a very painful way, and it went on to showing us that physics of the Earth is very, very important to understand all these data sets that we are collecting. Okay, so this is a summary, is that a non-mathematical discussion that we had of the reflections from simple ideal velocity layering that shows that the reflections from a step velocity function is the short pulse itself. Thin beds produce a differentiated short pulse, and beds which approximate a square pulse in velocity produce a pair of short pulses with a second delayed in time. And similarly, the composite reflection has its greatest amplitude when the layer thickness is 1/2, and the situation is called tuning. And the strongest reflections on field records result when the short pulse is tuned to the velocity, and ramp transition zones produce integrated short pulses. So, like I said, this was a short lecture, but it's very important. And I wanted to go over this before we switch to the next one. Anybody has any question? comment.
So, sir, yeah, the question is about the convolution. Just I'm curious, how this
Yeah.
who discovered that convolution will give us synthetic seismic? Was it just from mathematics, or was it
Yeah, from
some
the
geophysicists working on that?
signal processing people,
Okay,
electrical
sir. Okay.
engineers. Yeah, yeah. They thought about Earth as filters, so I might as well do that.
Okay.
That's yeah. Okay. Now, before I go to the next topic, I wanted to show you one assignment that I'm going to give at the end of the day today. But I wanted to explain this now, okay? And then you can. I will send you this notebook by email, okay? I'll send it to Ashok, and Ashok can then distribute amongst others, okay? So let's see here. Oh, are you able to see my screen, Ashok?
Yes, sir, I can see.
Okay, so here I have not given you any codes. So this exercise is essentially for you to be able to illustrate some of the issues regarding resolution and composition of reflections, just like the ones like the paper I just discussed. Okay, so there is this thing, seismic wavelet, then we have composite reflection events. And the first exercise is I have this Earth model. Okay, very simple Earth model. This is I think we have VP, thickness VP and density. And what I'm asking you to do is to, given this model, use the Ricker wavelet and the convolution model to generate post-stack synthetic seismograms. Plot the model, plot the reflectivity series and seismic trace together. Now you generate several traces by changing the peak frequency of the wavelet and plot those here. Okay, and to start with, you can use 20 hertz Ricker wavelet, and you need to describe the synthetics in terms of resolution of the layers. Okay,
Yeah.
and you can start to write your code here. And the second one is that I have a stack of layers. Okay, so here this model has a suite of sandstone layers within shell, and that will show you how effect of changing layer thickness is shown up on the synthetic seismograms, and you can see these layers are different, and you need to vary the wavelet and see how it affects the seismograms, and then changing one of the parameters, you can also see what that looks like. Okay, so all you have to do, the algorithm is given in the lecture notes. All you have to do is to convert depth to time. Then you have a time domain representation of the reflectivity, and all you do is convolve with the Ricker wavelet at different frequencies and make those plots. And there is a particular website, I will mention that, where you can actually even get some help with Ricker wavelets and a few other things. Even if you don't want to write the code, if you have the code available, just run those just to teach yourself what that looks like. Once you learn how to run it, then it's up to you to basically change those frequencies and to understand what is going on. And then finally, I'd like you to generate some angle traces for these angles and plot the angle gather. And I'll explain to you how to generate those. Same code with little change should be able to do this for you. You have to just use angle dependent reflection coefficients here. Okay?
Okay, sir.
Okay, so I have one lecture on travel time calculation, another is directly on seismic modeling. So I'll probably do the lecture 8 first, okay?
Okay.
We'll talk about travel time later on. Okay, now it's a good time to look at a little bit more detail into the modeling aspect of it. we started with convolution, and we'll see some other approaches. Okay, so what is seismic modeling? Seismic modeling essentially means solving wave equation for different kind of media, and I like to group this into two categories. One is analytic method, and another is numerical method. The analytic method means you have closed form solutions, and I showed you Green's function for homogeneous medium. That is the solution of your wave equation. I mean, you can do that for elastic also, but I just wanted to make it simple and showed you only for the acoustic case. Now, within analytic, we can have different categories. So, modeling or solving a PDE is not a new problem. It's been something that almost every scientist or engineer stumbles upon at different stages. And so given a particular problem, like we have, del T square P equals is equal to some source term, right? And in our case, this V is a function of X. It could be a function of T also, because if there is an attenuation, then you can make this frequency dependent, but let's not worry about that. It's a function of space. So as soon as this becomes, medium becomes inhomogeneous, your solution cannot be easily computed. For a homogeneous medium, you can get analytic solution. For inhomogeneous, you can get some kind of approximate solution, okay? If you want analytic. And for the approximate solution, we have ray theory, then some variants of ray theory like WKBJ, Gaussian beams, Born, and so on. And then there's a bit more accurate term, is called more exact. And here we have reflectivity method. Okay. So to get an analytic solution, you have to either get an approximate solution or you have to approximate the medium. Okay, or assume simpler model. So what I showed you here in the asymptotic solutions, the medium can be complex. I mean, it can be laterally heterogeneous of whatever heterogeneity you want, but then you can get a high frequency solution like ray theory. On the other hand, you can also think of this as layered medium, all flat lying layers, and then you can solve it in frequency wave number domain, and there you have something called reflectivity method. And of course, there is an extension for coupled, which is called coupled wave number domain. It's not very popular. The math is very interesting though. And there was one method that was used by earthquake community a lot. It's called Canier-Duhoop. I haven't seen it used much in exploration, so we'll not talk about that. And then pure numerical method. So pure numerical method basically allows you to keep the heterogeneity in the medium and then solve the wave equation numerically. So there we have finite difference, finite element, etc. So during the course, we will touch upon reflectivity, more details on reflectivity and finite difference, because these two methods are most popular in exploration seismology. And I will also talk a little bit about ray theory and Kirchhoff and Born later. I mean during this, but not today.
So one question,
Okay.
sir.
Yeah.
Yeah. So sir, remember that Helios software which I shared the thesis with you.
Yeah. Yeah.
So which method does that software use? Is it Born integral or The same
It's
reflectivity method.
no, it's Born series,
Okay, it's a bond series.
and
Okay.
I will discuss that definitely.
Okay.
Okay. Yeah.
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 Thank you, sir.
Yeah. Okay, so this is a very important figure that tells you different classes of solutions that you can get. So, do you want to approximate the medium, or do you want to get approximate solution, or you want to bite the bullet and do pure numerical? But I warn you, numerical solutions are also make use of approximations. Okay. As soon as the medium becomes inhomogeneous, you have to use some kind of approximations. Okay, so last week we talked about different hierarchy of wave propagation model, like anisotropic, elastic, constant density acoustic, and acoustic and stratified. So you'll see this 1D stratified media, then quasi 1D, 1D plus corrections, then you have 2D and 3D. So these are the wave equations. Now you remember what these are. But tell me, what is tau? This equation. What is u? Well, first of all, what is rho? Everybody should know what
Rho is the density, sir.
Rho is the density, and u is the displacement, right?
Yeah.
And
it's
two
the
double,
displacement. Yeah.
and two double dot means second derivative. That means it's acceleration, right?
Yeah.
This tau is the stress, and this is the body force. And so this is your Newton's second law, and that's your stress strain relationship. And this gives you the wave equation. So this is for the elastic model. Now we have two parameters, lambda and mu, and rho. And then we have this constant density acoustic wave equation. Okay. Okay. So we briefly talked about amplitude in terms of normal incidence reflection coefficients, right? So we need to understand like what causes variation in seismic wave amplitudes. So the first question that I'm going to ask you is, you go to the field, you collect some seismic data, and you plot the short gathers. And what are you seeing there? You're seeing some wiggles, right? So what do they represent here? What kind of plot are we getting here? So this is your time axis. This is particular location, offset. And what is this here? So that is changing.
Yeah, it is changing because of the. Yeah, please go ahead, Santosh.
Is it because of the ground change in ground motion or the ground response with respect to time? That's what.
So what physical variable is this? We call it amplitude, right?
Yeah.
But what is amplitude?
So is it? It depends on the receiver. What kind of receiver is there? Whether it is sensing the acceleration or just the velocity change or the pressure change.
Right. So those traces are measuring pressure in water or displacement, velocity, or acceleration on the geophone. Okay. So this is important. Oftentimes, we just treat those as wiggles and not knowing what actually you're measuring. And actually, in reality, in seismic exploration, we're not even directly measuring these. There's some kind of, we're basically measuring voltage, which is changing as a function of these. Okay. Okay, but these amplitudes, they don't remain constant, as we already saw from the homogeneous model. But now for inhomogeneous, this variation is even more complicated. There are a lot of factors that that affect the seismic amplitudes. One is source directivity. If you have an isotropic source, or if you have a vertical point force or horizontal point force, that will depend. That will decide, how the amplitude radiation pattern looks like at the source. Then we have spreading. Then we have reflection and transmission coefficients. We have attenuation. Then due to lateral heterogeneity, you can have focusing and defocusing, scattering, and also receiver directivity if it's a horizontal geophone or a vertical geophone. So these are the propagation effects, and these two are essentially from the instrument. Okay. So source and receiver directivity patterns are affected by experimental design and the instrument that has been used. And propagation effects are controlled by the nature of the medium, or what we call geology, right? So what kind of geological variation we have in the subsurface that affects the changes in rock properties, and the changes in rock properties are what are reflected in our seismograms as changes in amplitude and phase. So much of the seismic wave analysis is done assuming locally 1D isotropic Earth model. So now you know what is meant by 1D. So we will start with 1D wave propagation. Okay. So today we will take a more intuitive approach, and then next week we'll talk about more details of Kennett algorithm for 1D medium. But what we'll discuss today would be the basic building blocks for Kennett kind of approach. Okay, so let's say that I have a point source, and I have a layered medium. So each layer is homogeneous. It has p wave velocity, shear wave velocity, density, and thickness. And you can also have an isotropy, depending on what level of approximation you want. So in which case, you have 21 coefficients in general for anisotropy, then you still have density and thickness, and then you have attenuation. Okay. So what we want to do is to be able to compute the response at the receiver when a pulse is injected at the source location. And of course, isotropic and VTI has cylindrical symmetric. Okay, so first thing we need to understand is what happens at the interface. Okay, so let's say that I have a medium with essentially two layers over a half space, or there are two interfaces. So now this is one ray, it's the interface, and it gets reflected as P wave. Then can be conversion into shear. There can be transmission, reflection, and there can be transmission, reflection, another reflection, then it can be converted to shear. So all of these paths are possible. So how many paths are we talking about here? You can't count. It's infinite number. Okay. And each ray here is defined by its ray parameter, right? So the question is, how do we compute these paths, like travel time and amplitude modifications at the interfaces? Now remember that we are building the response from several plane wave responses. So if we know the response of each one of these, we sum those up, and that gives us the total response. Okay. The Kennett's algorithm allows you to not have to count all the ray paths. Okay, and still it includes includes full response. At the same time, it also can, if you wish, it can let you break it up into different paths. And I'll talk about that in the next class. But this is how the real scenario looks like. So, like I said before, each ray is defined by its ray parameters, and don't forget this. Let's just focus on isotropic medium. So ray paths are easy to compute, Snell's law, where horizontal slowness is preserved. We talked about this already. Okay, now I'm going to get into some nitty-gritty details of layered media calculation. So let's look at the primaries only model, okay? Now remember this equation, T equal to tau plus Px. So what is tau?
Now is the intercept time.
Vertical delay time, intercept time is basically simply two-way time, right?
Yeah.
Which is a function of vertical slowness, right?
Yeah.
All right. So now if I take the primary path, then as a function of P, I have tau, which is QP, 2 times H1 is the thickness, right? And QP is 1 over alpha square minus P squared. Similarly, for PS, we have a P path and we have an S path, right? And this is this. The same ray parameter for P and S, but the angles are different, right? And that is because the velocities are different. So, if we just considered primaries only, then we have one PP and one PS path, and the delay time is given by this. Okay? So, what we can then do is for PP, I multiply with a number, it's called RPP1. We call it P2P reflection coefficients without defining it yet, but I will define it soon. And for the PS path, I have RPS, which is the P2S converted wave reflection coefficient. Now, if I go to the second layer, then I have to take the transmission down. Then I have to get the reflection here, and then I have to get the transmission, and then I have to get the travel time. Okay, so the reflection time in tau p domain is going to be simply this, right? Tau as a function of p. So this way you can build the plane wave responses and sum them up. Okay, and then you do the tau p transform to xt domain plane wave transform, and that gives you point source responses. Is this procedure clear?
So for the amplitude, we are just multiplying the reflection coefficient with the delta function.
This delta function is for the timing, right?
Okay. Okay.
And then you can convolve it with the source wavelet if you like. Okay.
Okay. Got it. Okay.
Okay.
Yeah.
Yes. Good. So keep on asking things like this, because these are some details I may not remember to tell you, but okay. So here is my acoustic case in tau p domain for a single interface. Okay. This is your synthetic seismogram in tau p domain. Here I have used a Ricker wavelet. And at each time I have a tau and then reflection coefficient. So what do you see here? Let's be a bit more interactive, and some of the people need to come up with an answer. What do you observe here given this? There are at least 6 or 7 people in the audience, so everybody should try to Don't feel shy.
So
I'm
we
not
see
in.
that as the ray parameter increases,
Mm-hmm.
the 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 travel time is, I think it is decreasing,
Yes. Yes. Very good. That is the
because the
delay time,
sun,
right?
yeah,
Yeah.
because P is actually inversely proportional to velocity.
Right.
So the travel time is decreasing, yeah.
Good. Good. What else do you notice here?
And do we see the change in amplitude? I don't know whether the
Yeah.
amplitude is
Yes.
also changing.
Yeah. How is it changing?
It
It
is
seems it is
increasing
in, yeah.
towards, yeah, it is increasing actually from
It's
left to right.
increasing, right?
Yeah.
Yes. Okay. Good. So I take this now. I do a plane wave transformation and I get a point source synthetic. This is your offset gather. Okay. So what do you see here now between this and
So,
this?
yeah, it is just, I think it seems reversed. Now the travel time is increasing with offset and the amplitudes are decreasing with offset.
Is it decreasing right from the beginning or?
Uh, yeah, it seems so. It is decreasing from near to far.
Well, actually, it's increasing first and then it starts to
Okay,
decrease.
okay.
Anyway, it may not be so obvious. Okay, so why is there so much difference between this and this? Well, travel time, we can obviously understand because the px part is here, added here. Why is there change in amplitude between here and here? All right, first of all, why is there an increase in amplitude with angle here or P? Just guess. What factors affect amplitude? They go
So
back to
obviously
that slide.
this, yeah,
Go
can
ahead.
you, yeah.
Yeah, go
So,
ahead.
I mean, the delta function was there, right, sir? In the equation you wrote RPP into delta T minus something.
Mhm.
So is it because of that delta function that the amplitudes
The
are
delta
behaving
function
like
is
that?
the delta function is shifting in time.
Okay.
What other factor was there in the synthetic case?
The reflection coefficient also.
Good. So reflection coefficient is increasing with P here in this case. Okay?
Okay.
But then the scene completely changed here. It's now saying that there's some increase, but then it is decreasing. So what is happening here? Did we add a new effect here? We must have, right? Remember, this is a plane wave response, right?
Yeah.
And this is a point
So,
source response.
okay, for the point source, I mean, it is spreading out. The amplitude is
Very good.
decreasing. Yeah.
Good. Very good. So this one has spreading and this one does not have spreading. So here you're only seeing the effect of reflection coefficient, right? But here we have reflection coefficient effect as well as the spreading. Okay.
Yeah.
So that is why you see that in the beginning, reflection coefficient was dominant. So that's why you were seeing increase with offset, but later on spreading is dominant. So now it's decreasing. Okay.
So
Okay.
in the Taupi case, why is the reflection coefficient behaving like that? Is it? I think it is not very obvious from the equation in the
Oh,
Taupi
because
case.
the reflection coefficient is a function of VP, VS, and rho, right, of the two layers.
Yeah.
So whatever the reflection coefficient is, it's actually picked that up for that particular model that I have.
Okay.
Okay. Now we'll look at the elastic case. And in this case, we have an explosion source, but we have, what kind of source I have? Explosion source and vertical and horizontal receivers. Okay. So this is the vertical response, and this is your horizontal response. This is PP. Okay. Now this is important because this is the same kind of model. So there's a reflection coefficient increasing with P, but there is a receiver directivity. This is the vertical receiver. So vertical receiver responds to rays that are coming more vertically, and horizontal receivers get more amplitude when it goes to the rays, when the rays become more horizontal. And that is why you see that at small p values, the horizontal response is very, very small, but at very large p, you're seeing some response of the, you're seeing some significant amplitude in the horizontal component. So this has two effects. One is the effect due to reflection coefficient, another is the effect due to the directivity of the receiver. Okay. And so if you're doing land data IVO, this is something that you have to remember, that there is a directivity effect in here. Okay. And one other thing people say that
Sir, just a small doubt here. So when you're saying this directivity effect of receivers, I think basically in land data, as you mentioned, that happens from the 3C component geophones and all might be required to be used. But in marine also, like in a conventional streamer, I don't think so we get to use. Maybe we have to go with the nodes and all. Is that the approach for it address this?
Yeah. In marine case, if for pure, your hydrophone data is pressures. It's independent of there is no directivity, so that is not important. But if you have the node data where you have elastic effects and you have, if when you have what do they call it, 4C, right? The 4C, the hydrophone has no directivity, but all those geophones, they have directivity, so that has to be taken into account.
Okay, sir. Thank you.
Yeah? And if you just transfer, convert it to XT, this is what it looks like. And now if you have shear waves, you can see P2S conversion is very, very small. P2S conversion is 0 for normal incidence for P wave, right? That's why you don't see any shear here. And this is the shear wave arrival here, and this is the shear wave. And you can see very clear difference in the move out, right? And why is that?
It is because the shear velocity is slower than the P.
Exactly.
And the curvature depends on
that.
On the velocity. Yeah.
Yes. So if you convert it to offset time domain, you're seeing something like this. Okay. So this is very important also to understand directivity and the reflection coefficients. You can see PP is small, almost negligible at zero offsets. It's actually 0 at zero offset, but we don't have zero offset here, but close to zero offset is very small. At the same time, S to P conversion is also very small, near zero offset, and S to this is S. Okay.
Yeah.
However, now I put in all the multiples. This is simple one layer model. So you can see this is P, this is S, this is internal multiple P, internal multiple S, and so on. The two components. So if you have a strong reverberation, this is the full multi-component synthetic seismograms for P and S. So this is, I should not call it PP or P wave receiver or S wave receiver. This is the vertical receiver and this is horizontal receiver. In the industry, people say, P wave receiver, S wave receivers, but typically they mean vertical and horizontal. But in vertical component, you can have shear wave also, and in horizontal component, you can have P wave also, depending on how the rays arrive at the receivers. Okay. So this part will go in detail next week. But for now, what we need to know is something that I have not gone into details of. So we have to be a little bit more rigorous in describing how we went about doing this. Okay, let's bring in some rigor. Okay, so I go back to the same model. So how do you compute reflection coefficients first? So for that, we have to consider boundary conditions. Okay, when the waves hit an interface, what happens to it? To be able to understand that, again, we go back to the basic equations. So let's say that I have an interface here. This is for medium 1, and this is medium 2, and this is my normal direction. And we consider a small box here. It's called pillbox. And consider the total forces. Okay, so body force, initial force, and surface forces. That should go to 0, right? Otherwise, the medium will collapse, right? Depend on what you're looking at, which way. So some of these forces should be equal to 0. So this is your Newtonian state, Newton's second law of motion, and this is from the stress component. This is the traction. Some of those should be equal to 0. And then you can write this traction term, and you can say that this is very thin, so I have only the top interface and the bottom, the top and the bottom of this. And this is the upper surface, and this is the lower surface, and the direction of the normal is opposite to one another. And then what we have is that the normal component of stress in the upper surface should be equal to normal component of the, I'm sorry, this one should not be, yeah. Okay. So stress is continuous across the boundary. So what it means is that tau lower dotted with z hat, which is the normal direction, is equal to tau upper. Okay. Now, if the upper medium contains no materials, then this is equal to 0. So that's my free surface boundary condition. This is the solid-solid reflection coefficient. Solid-solid boundary condition. For the liquid-solid case, we know this is correct. Now, another condition we impose is anti-cavitation. That means the velocity or the displacement, vertical component of displacement should be same as the vertical component, both solid and liquid case. This is solid layer, this liquid layer, say for example, this is ocean water, and this is your sediments. So there, boundary conditions are modified. Okay. So for a solid-solid interface, we have this is equal to this is equal to this. However, we impose another condition that the two layers are in welded contact. That means they're not allowed to move sideways. Okay. So what that means is that all components of stresses, all components of velocity, displacements, and normal components of stresses are continuous across the boundaries. And the reason we want to understand these boundary conditions is because we want to be able to compute reflection coefficients which come out naturally from these boundary conditions. So let's follow this procedure given in Aki and Richard's book. And he actually did it in terms of potentials. And when I talk about Kenneth method, there is one other way of doing deriving reflection coefficients, which I'll discuss next week. But this is the most popular ways that people derive reflection coefficients. Even in Zopri's original work, you'll find this. So define the plane waves in terms of potentials. Then you consider incident plane waves with unit amplitude. It's important that you stick to plane waves here. And express displacements and stress components in terms of these plane wave potentials. And then you apply boundary conditions of continuity of stresses and displacement. And that gives you a system of equations which you can solve for RT coefficients. So this is typically all the coefficients that that you can get out of the whole operation, of the whole process that I talked about in the previous slide. You can have an incident P that gets reflected to P. This is PP, this is PS. This is PSB system, this is transmitted P, this is transmitted S. There could be incident S, reflected S, reflected P, transmitted transmitted S and transmitted P, and the angles are different as we talked about. So similarly, there can be incidents from the top, there can be incident from the bottom, and we have similar picture like this. So these are different coefficients that are calculated using this whole procedure. So we have these elementary formulas for reflection and transmission coefficients. Okay. Again, I don't want you to look into details of this, or maybe you're not even able to read it on the screen, but all that I'm showing you is writing these displacements in terms of outgoing P, outgoing SV, and so on. And then we look at the scattered field, like upgoing P, upgoing SV, the same picture that I showed you. And here we're using these coefficients PP, PS, SP, and SS, which are unknown. And these are the ones that will be solved for from the system of equations that we derive. And that system of equations will basically result from the boundary conditions. Okay, so you have these different plane wave potentials, and then you can convert those to stresses and displacements, and you can get a scattering matrix which looks like this. Okay, and remember this symbol, this is down up. Okay, and P and S is obvious, and we're talking about PSV only. SH is totally decoupled from here. And then you get a matrix equation, and this is basically the equation for reflection and transmission coefficients. Okay, so this is not as complicated as it looks. It's kind of easy to program. This is Zopr's equation. And, almost every company, every academic institute has these codes for computing reflection coefficient. These are what we call exact reflection coefficients. So what did we learn here? Well, the first thing that we learned is that the reflection coefficients are defined for plane waves to start with. Okay? And therefore, these are functions of P, ray parameter, which can be converted to angle given the velocities. So just to tell you a little bit about this, when I went to graduate school, my very first semester, my advisor gave me some problem to work on, which I was working on. Then one day he came to my office and says, Ronald, can you write a code for plane wave for reflection coefficients using this Aki and Richards formula? And I wrote it, and it was working fine. So then one day he called me and says, well, one of our colleagues, he wants to use this code of yours. So can you give it to him? So I said, yeah. They said, oh, no, this is not going to work because Aki and Richards equations are not valid for liquid solid case, and he wants to compute reflection coefficients at the seafloor. Then I said, no, it works for liquid solid case. And he says, no, it does not. Then I said, yeah, and the actual formula does not work, but then I actually made some small changes to it, and so it's working. And he thought I was a genius of some sort, but I was not. He was a very smart guy. In any case, if you try to code this PP reflection coefficient, you will find that there is an instability the way it's written for acoustic elastic medium, but you can move some terms around. And then many years after that, maybe 10 years after that, I was consulting for a company. I won't name the company, and then would my task was to build some synthetic seismograms for them for converted waves, and they had like five different codes for reflection coefficients, and it was very unfortunate that none of them were correct, because they was not giving the amplitudes at the correct reflection coefficients. So this is a key to understanding wave propagation, and you have to be very, very careful, not just to understand this, not just about understanding this, but also about implementing this. So make sure that you have implemented it right, and once in a lifetime you should do that, so that you have the exact reflection coefficient somewhere, which you can basically benchmark against, or other algorithms can be benchmarked against that. So having said that, I will then make a few more comments on this. So this is exact Zopr's equation, but very few people actually, I mean, in an industry, it's not that popular, because initially it was told that it's complicated, but now for other reasons. First of all, this is our case, right? We have interface, we have P2P, P2S, and this. So we have an incident plane P wave, we can reflect it P and S. So if you look at Archian-Richards equation, this is what it looks like, okay? You can code it very easily. Nowadays, with Python, MATLAB, this goes very easily, but we had to write everything in Fortran many years ago. But here, what you see is that it's not difficult to code, but there's one problem. Well, first of all, is this a real number or a complex number? Is the reflection coefficient always real, or can it be complex? Anybody?
Sir, I know
Okay.
that reflection coefficient is -1 to +1.
That's for that's the absolute amplitude. So what happens is that it's a function of P, and so P is here, sine theta over V, right? And Q is equal to 1 over V squared minus P squared, right? So what happens is that when P becomes greater than 1 over V, then Q becomes complex, right? So when does it become greater? So for example, when we have, let's say that we have a ray that is being reflected, right? And there is a transmission also going on here, right? As you increase the ray, then what happens is that this transmitted ray becomes more and more horizontal, right? If the velocity is increasing, there is one point where it actually gets completely reflected, okay? So beyond that, your P becomes larger than 1 over V, because this is your 1 over V. This is the critical angle, right? And there Q becomes complex. And in that case, what you have is something called evanescent waves. And there is a phase change in the reflection coefficient. So your Zopr's reflection coefficients are complex. They are real only within pre-critical zone. There's a complex, they were complex in post-critical, okay? So you will see a change in phase as you go to post-critical, okay? Now, that's one thing. The second thing is that even though these are exact reflection coefficients, if you just look at these equations, they don't, this equation does not provide you with much of an insight, in the sense that what happens when I change the velocity, if I change the shear wave velocity, I change the density, how's my amplitude going to change, right? So with that in mind, this is said, this is in Archian-Richards book. It's called linearized reflection coefficient, but I think it was done by some other people also. But anyway, so in Archian-Richards case, what they did is they assume that the contrast in velocity and density are very, very small. And then they use the average velocity, P wave velocity, shear wave velocity. And this is the contrast. So essentially what they're saying is that my alpha 2, which is VP2, is equal to alpha 1 plus delta alpha 1, where delta alpha 1 by alpha 1 is very, very small. Okay? So for small contrast, then you can derive this equation. Now, this equation is actually quite interesting. And the reason it's interesting is that now you can see how changing the velocities and densities can affect the reflection coefficients, right? If I can say that if I change P wave velocity by 10%, by say 2%, how much is the amplitude change as a function of P? Similarly, I can do that for shear and so on. So this is where linearized reflection coefficients become quite useful because it's much easier to interpret, but with the caveat that this is valid for small contrast, okay? And what does that imply? It's always real. There is no complex reflection coefficient for media with small contrast because it never gets post-critical, right? It never gets critical, it's very small, right?
Yeah.
So then Shui came up with his own form of linearized version of reflection coefficient, and this became actually quite popular because he wrote it like this. Now, the first term is the normal incidence reflection coefficient, and then there are some angle dependent terms. So this is a two-term, so you can think of this as A, B, and C, a three-term AVO. And so you can see very clearly that in R naught, which is essentially your normal incident reflection coefficient, there is no shear wave. So this is totally independent of shear wave. And sine theta value increases with the value of theta. So this is where the Poisson's ratio effect actually starts to show up. And once we have that equation, now we can put in different scenarios, different sand shell layers with different amount of fluid in it, and then see how the Poisson's ratio is changing and how that is affecting your reflection coefficients. Okay? And
one question.
Yeah, go ahead.
So we assume that, there is an assumption that the contrast is very small, but
Yes.
still, based on that equation, we find anomalies, and anomalies are known to have higher contrast. This is something very, we are able to do it somehow, but the equation does not. The assumption is something very different. So what is the implication of all this?
Yeah, so there are two things that are happening. Is that one is the small contrast, and another is small angle. Okay, so the effect of the contrast you see much better. You go to higher and higher angles. Okay, since we restrict ourselves to smaller angles, I think we can get away with a lot of these approximations. Okay. Yeah, very good question. But let me see what. So we can write this as A plus B sine squared theta plus C tan squared theta. So using this equation, people made use of AVO analysis and made some interesting discoveries and a lot of failures also. But this became a very powerful technology and was in use for quite some time. I think it's still used. So you correct the CMP gathers, and you can transform the gathers to angles. So these are all angles, right? And then you can fit this curve. Okay. So you can derive A and B, and people made lots of money by showing how A and B actually changes for different kind of lithology and fluid. And there has been also debate as to whether we should use C term also. And that allows you to go to higher angles. And of course, that does allow you to go to higher angle, but then the problem is that at high angles, that amplitude is not so reliable because you have NMO stretching as well. So this is all applied to NMO corrected data. Now that we understand reflection coefficients, so this can be then used to generate reflection coefficient as a function of angle, right? So this is for normal incidence, and if you just use two terms, that will give you reflection coefficient as a function of angle. And here we can then use simple convolution model. So all that we do here is we use the wavelet and we convolve with angle dependent reflectivity. This T is the 2A time of the reflector. So synthetic trace would be a convolution of wavelet times this. Now one other thing that is done in industry is they use angle dependent wavelet also. And one of the reasons, or rather one of the justifications that is given here is, I've heard different justifications about this, but one justification was that, oh yeah, because with angle our Q effect comes in, and so we have to, typically if you just determine statistical wavelet from angle stacks, you will see that the wavelet becomes broader and broader, missing high frequencies. And so is it really Q effect? I don't know, maybe, but I think the one other factor that really comes in more strongly if you go to high angles is the effect of NMO stretch, which is essentially making the reflection lower frequency. So in any case, for practical application of angle stack inversion, it's very common practice. It's a very common practice to use an angle dependent wavelet also. So otherwise, it's the same as the convolution model that I showed you for the post-stack case. So the assignment that I gave you, where the first part is for post-stack synthetic seismograms, the same code you can use for angle traces simply by using angle dependent wavelet. You can also try to use lower frequency wavelet as a function of theta, but for synthetic modeling experiment, it is not necessary. So the idea behind angle gather generation is simply synthetic angle gather is simply the convolution of wavelet with angle dependent reflection coefficients. So the steps are you build out model, so VP, VS, and rho for layer, and I already gave you a layer stack. Then you choose wavelet. It could be Ricker or Ormsby or whatever. Compute RT theta. It's very easy to write a code to do that. All that you have to do is to include this part in your normal incidence case and do the convolution. So then you have, for each theta, you get one trace. So let's say that I have 10 layers. So I have 10 different reflection coefficients for the same angle, convolve it, and then I get the angle trace. So 5, 10, 15, 20, you can use it for different angles. So for example, here we have a shale and sand layer, and there is some anomaly in this reservoir. This is the sea base, and then you can compute reflection coefficients. So this is your R0, and this is the gradient, and then you can compute your angle traces. Okay. So this is one example. Here we have the shell. This is the gas sand. This is the shell. So you have this reflectivity and that reflectivity. So this is your negative and this is your positive, and you can actually see how this is going. And if you follow this carefully, you can see that there is an increase in amplitude. If you just plot the amplitude, this looks like this, more and more negative. So this is your typical class 3. So one of the things that you have to remember is polarity convention. Now, this is your American convention, negative contrast, or the drop in contrast, negative change in the impedance basically corresponds to negative polarity, but in European convention it's the other way around. I don't know what convention is used by Reliance.
We follow the SEG standard, sir, same as what you have shown.
Okay. So SEG standard is normal is the hard kick positive. Okay.
Yeah.
So we have to be very careful when you're comparing with real data. And then, of course, keep angles less than 40 degrees. Okay. It basically, because the approximation itself breaks down beyond that. Okay. Now, for anisotropic case, it's actually quite a bit involved, because if you look at Shui's equation or Rogers' equation, Ruger's equation, it gives you the formula for also AVO equation. But remember, this angle, as soon as you talk about anisotropy, the question would be, are you talking about phase angle or group angle, right?
Mhm.
So you have to be, when you are doing it, remember that these are all valid for the reflection coefficient is a function of P. It's talking about phase angle. Okay. So when you apply a Ruger equation or any other kind of, or even for HTI medium, AVO, then you have to make sure that what you're using is actually phase angle. Okay. And then you can look at tuning thickness, the noise in the data, and all other things. Remember, the convolution model is 1D. Okay. Okay, so here is a little sort of snippet of a code for generating angle gathers, and this is the library that you can import. Okay, and if you can just search, and you can go to that GitHub site, and you can find a lot of very useful code. So for example, Shui, all those functions are already given there, recur and all that. And they may even have codes for generating synthetic seismograms. So feel free to use those rather than writing your own. But I think at some point in your lifetime, you should try to write code so that you are able to appreciate every term that goes into your code. Okay. So this is the same figure that I showed you earlier, an offset to angle gather, and then. So I wanted to show you some comparison. Okay. So we have shale, gas sand, brine sand, and salt, and AVO curves. And what you see here is that there's a relationship. There's a exact is the red with the full Zopler's equation, and the green is the linear approximation. And you can see that for some cases it even breaks down at around 30 degrees. But other cases it may actually go all the way up to 40 degrees. So you have to be a little careful. So typically I don't recommend going beyond 35 degrees in using angle type of inversion. Okay, so this is something that motivated all the studies of AVO. This is a paper by Rutherford and Williams. And after this paper was presented at ACG, AVO became a hot commodity for the whole seismic technology people. So here we have different kinds of AVO curve, and this one shows like class 1. These two are class 2, and this is class 3. Class 3 is for gas sand, where actually you see this becomes more and more negative as a function of angle. This is a function of angle. So the significance is that the view curves can be loosely divided into three classes. This is class 1, high impedance sand. Class 2 is nearly same as shell impedance. Class 3 is low impedance sand. So class 1 has higher impedance. The main purpose of showing this is that all the math that we did so far is not useless, okay? And there is a motivation behind this. We geophysicists are practical people. We do all the math that will bring us some value in finding oil and gas, for example. So you can see that the simple math that we did can help us distinguish between different types of rocks. So in class 1 sand, they have higher impedance than the encasing medium. So here reflection coefficient is positive at zero offset, and it decreases in magnitude with offset. It can change polarity. And this was theoretical, but is it really observed in the data? And you can actually see that they put it in their paper. You can see a stack section, and this line is over channel sand, and this is the production interval, which is marked by this box. And this shows that because AVO changed polarity, when you stack this, they cancel in amplitude, and this looks like no reflection zone. So if you look at this particular gather here you can see how the amplitude is changing and the polarity is changing, and when you stack, it shows a different character altogether. And this is from the data. These are the gathers from the field data, and you can clearly see how the polarity changed. And here, if you stack those, obviously you're not going to get a good amplitude. So this led to some important discoveries many years ago. Now class 2, this sand has nearly the same impedance as encasing material. These are moderately compacted and consolidated. Normal incidence reflection coefficient is nearly zero. A large change in reflectivity from near to far offset, and reflections seem to suddenly appear at large offset. So, and the polarity change may also occur. So here shows you migrated stack section from a Miocene gas sand in Brazos officer, about 2.1 second. This is the one. Now, if you look at these gathers, so these are different panels. This is 5 degrees, this is 14 degrees, this is 22 degrees, this is 29 degrees, and this is 37 degrees. And you can see that the angles, so you can see that for each 1 second window, how the amplitude is changing as a function of angle. And this is, of course, offset. You could have shown those as angle gathers, but this is one other way of displaying it. Class 3 is what became the most popular because it has lower impedance than the encasing medium. So then you have amplitude increasing with offset, becoming more and more negative. And even after stacking, you don't see a catastrophic effect because they basically stack up in phase. So you can see very bright reflections, and this is one such data. This is a gas well, and you can see beautiful bright reflection in the stack section. This is from High Island area of Gulf of Mexico. And this is beautiful data set. And 5 degree, 14 degree, 22 degrees, 29 degrees, and 37 degrees. You can clearly see how the amplitude is increasing with offset. It's almost like synthetic seismograms. I don't have access to this data. I would have liked to play with it some more to make better displays, but this is a very old paper, and that shows you really how the amplitude changes in the real data if you're careful enough with the processing.
So we have a very exact similar case here in east coast of India. in Miocene sands. So they are typically
Okay.
class 2. You're not able to see it on the nears and mid, but
Yeah.
when we move to the higher offsets, we start looking at those bright spots. Quite interesting, yeah.
Yeah, yeah. So yeah, this is right. So AVO gradient and intercept, they can be used to classify different sand bodies, and they become a very important tool for quantitative interpretation. That's where it started, some maybe 20 years ago. But now it's even more advanced. We're doing AVO kind of inversion and doing a lot of other things because software is much fancier, data collection is also more sophisticated, and also the processing steps are also quite mature. So it's very important to understand amplitude variation, not just the travel time variation. So this is from Afsed's book. So you have the stack section, you have the CDP gather. Just excuse me. This alarm in the house basically gets turned on for no reason. So you have this AVO response, and then from there you can do a lot of different analysis and interpret those in terms of subsurface geology. Okay. So I hope you got a good flavor of how the amplitude affects your seismic interpretation. And seismic inversion is not something that I've talked about, but this is for a very simple explanation, even though that simple thing, like we started from post-stack, and you saw that even the post-stack case, interpreting the seismic traces is not trivial because of the interference and all that. Then we went to angle stack, and we talked about reflection coefficients and somehow the synthetics are computed. And I've given you all the basic ingredients for generating synthetics, except for the fact that I haven't told you how to get full synthetics, which we'll talk about next week. Okay. So I stop here and take any questions. We have about, I think we should leave some time for discussions, not just me talking one-sided.
So, sir, you will be covering that Born integral. I mean
Yeah.
Okay.
Sure.
So apart from the Kenneth, you will be covering that.
Yeah.
Equation.
Also find. Yeah, and also
Okay.
find a difference. Yeah.
Okay.
So we still have a lot of topics, but if we do everything in one day, then I have to rush.
Yeah,
And then
right. I understand.
I wanted to do the basics first, and I think we have gone. We have gone through the most important stuff, and then next thing would be this. So
Yeah. So one question regarding, sir, that constant density. When you say that people are using FWI, assuming density is 1, and keeping velocity as the factor. But I was just experimenting with FWI using DeVito, and I started with this constant density 1, but somehow just below the seabed, it was updating a lot. Abnormal values. I mean, it was not expected because below the water, we want the velocities to increase, but it was decreasing. So I don't know whether I was correct or I was doing something.
No. I think you made a very good observation. In fact, I found the same thing because in the right at the seafloor, it could be decrease in density, and then that is not reflected if you fix the density. So one of the things you can do is to not make it 1 right below the seafloor and see what kind of velocities you get.
Yeah, I started then.
It's trying to trust the amplitude 100%, and it's trying to find a parameter that will better explain the amplitude. And in that process, what happens is that it puts everything onto velocity because that is the only variable you have. Okay.
So practically, sir, especially in marine cases, we should not do constant density FWI formulation.
It depends, like it depends on the depends on what you have. But doing a variable density FWI is not a problem actually.
Yeah, I
You can
started.
also-
Yeah.
Yeah.
In the second iteration, I started with the variable density. I will be getting
Yeah.
the results on Monday, and I will compare how it goes.
Yeah, another thing is that you don't have to solve for density. You can give it a density profile that is different from one. It can be depth dependent and fix it.
Yeah.
Okay. And the other possibility is also use some kind of empirical relationship between VP and density.
Right.
Okay.
Right.
Because if you want to, sometimes density inversion is unstable. So you may run into some other difficulties if you use a variable density FWI.
Okay.
So you have to try all of these different things. Anything else? If not, I think this is all I wanted to cover today.
Yeah.
So I can send you that notebook, which you can pass on to different people. In fact, we'd like to talk about that next class.
Yeah.
And we
Great,
have
sir.
done it.
And
Yeah.
also, sir, will you be able to share your slides as well? I mean, it would be a
Yeah,
good
sure.
reference point. Yeah, that would also
Yeah,
be
I
good.
can- Yeah, I'll send you
Great, sir.
those. I'll send you those by email.
And also, sir, a few references. I mean, there are students also
yeah.
they'll be interested in
Yeah.
reading out. So some
Yeah.
good references so they can read it in their college. That would be good.
Yeah. I'll give it to them. Okay. Anything else you guys want me to discuss today, or?
No, sir, I think it is Santosh. Do you have
Nothing.
anything in mind? Okay. Great.
Nothing as such, I think.
Okay.
Need some time to digest and then
Yeah.
maybe next class.
Okay. Yeah. Okay.
Okay. Yeah, like I said, if you have any questions, just send me email even before next week. So before
Sure,
the
sir.
next class.
Yeah. Okay, sir.
Thank you.
Okay.
Yeah. Thank you, sir.
Have a nice
Thank
weekend.
you for that. Yeah.
Okay.
Bye-bye.
Thank you, sir.